Hello everyone, this is Ghaith and I am super excited to present to you our work titled A Compiler Framework for Optimizing Dynamic Parallelism on GPUs. Let's start with some organization. A typical program running on the GPU is usually called a kernel, and a kernel is essentially a set of threads which are the workers, if you will, that would be executing the parallel work on the GPU. These threads are organized into thread blocks, are grouped into thread blocks, and a collection of thread blocks is called a grid. Dynamic parallelism is a feature whereby it enables threads executing on the GPU to execute and launch other grids of threads. This is useful for implementing computations with nested parallelism. However, in practice, using dynamic parallelism may cause many small grids to be launched, and launching many small grids causes performance degradation due to congestion because devices do have limitations of how many grids they can execute simultaneously. So when we do launch a huge amount of small grids, eventually some grids are going to have to wait. Instead of executing in parallel, they would execute serially. Also, hardware underutilization. So if we launch a lot of small grids, there might not be enough threads launched to fully utilize the hardware resources. The solution to this problem is launching fewer grids of larger sizes. Prior work, one optimization that is done by prior work is called aggregation. Aggregation is an optimization whereby multiple child grids are consolidated into a single aggregated grid, and one parent thread launches the aggregated grid on behalf of the rest. So for example, let's take this example. Here we can see 4 parent threads. Each one of them does a dynamic launch and launches its own grid. So we end up with differently sized grids. We apply optimization, we apply the aggregation optimizations. Now we have 4 parent threads. They work together in order to consolidate their work. And once they are done consolidating their work, one of them does the aggregated launch, which is a larger grid with all the work of the parents combined. This tackles congestion and reduces it by reducing the total number of the launched grids. It also improves utilization because now the aggregated child grid have more threads than the original one. Aggregation that has been done by prior works at aggregating the grids at several levels of granularities. So take, for example, this original kernel. The first granularity is called warp granularity, whereas every warp within a grid would consolidate its launches, and one thread from this warp would do the dynamic launch. So as a result, at most, per every warp, there would be at most one dynamic launch. A more fine-grained or a more granularity that aggregates more aggressively is block granularity. In the block granularity now, for every parent block, all the threads in this parent block are going to consolidate their dynamic launches, and then one thread from the parent block does the dynamic launch. So as a result, in block granularity, we could have at most one dynamic launch per parent block. And finally, we have grid granularity, which means that all the threads in the parent grid are going to consolidate their work into one launch. And then finally, there would be one launch with all the child grids aggregated into one larger grid. Our contributions, we present thresholding as a compiler optimization. Prior work relies on programmers to apply thresholding manually. Coarsening of child thread blocks. Prior works on compiler-based coarsening is not specialized for dynamic parallelism, so we introduce it in the context of dynamic parallelism. aggregation of child grids at multi-granularity. Prior work only compiler-based aggregation only considers core, block, and grid granularity. So there is a space between all of these, between block and grid granularity that has not been evaluated before. And then we introduce our compiler framework that combines all of the three optimizations together. We start with our first optimization, which is thresholding. So thresholding is an optimization whereby a grid is launched dynamically only if the number of child threads exceeds a certain threshold. Otherwise, we execute the work sequentially by the parent thread. So let's take this example. Here we have 4 parent threads. Each one of them discovers some work and does a dynamic launch. Now we apply the thresholding optimization. Here we need to set some kind of threshold where if the number of threads is less than a certain amount, we do not perform the launch. If we apply the optimization here, we can see that the second and fourth parent threads does not have enough, their launch does not have sufficient amount of threads, so their works are serialized to the parent thread because they are small. Thresholding reduces the congestion by reducing the number of the launched grids. It also improves utilization by only allowing grids with many threads to be launched. So how do we achieve the thresholding? We apply the following code transformation. We create a serial device function that is executable by the parent, which represents the same parallel work done by the child. However, now it's done serially. We also make use of a heuristic to detect the total number of threads to be compared with the threshold. We detect the number of threads to be launched by observing commonly used grid dimension calculation expressions, such as Seening divisions. So we would typically look at the grid dimension. We've observed that a lot of programs of GPU kernels, they would use a lot of commonly used expressions. We look at these and try to detect the number of threads out of these commonly used expressions. Finally, we apply a conditional guard to decide, so that the parent would decide to either do the launch or serialize, and that is essentially dependent on the set threshold. Next is coarsening. So coarsening is a transformation whereby the work of multiple child blocks is assigned to a single child block. So here we take this same example again. We have 4 parent threads. Each one of them does a dynamic launch. We have grids of several block sizes. We apply coarsening, and we can see here the original thread block before coarsening, and now they are coarsened. So one block is doing the work of 2 essentially. For this optimization, when it is applied before aggregation, it amortizes the costs of disaggregation. How do we achieve the coarsening code transformation? We create the coarsening child kernel, which is by inserting the coarsening loop around the child kernel body. Then we modify the kernel parameters and modify the launch parameters to accommodate for the newly transformed kernel. We also apply our third and last optimization, multi-block granularity aggregation. It is an optimization whereby the child grids of multiple parent blocks are consolidated into a single aggregated grid. So we take this example where we have 4 parent blocks, each a certain number of threads do dynamic launches. We apply the aggregation, the multi-block aggregation optimization. Now, for every 2 parent blocks, we are consolidating the number. So in this particular example, we are aggregating for every 2 parent blocks, we are aggregating their launches. So in this case, they aggregate their work, and one of them executes the work, and one of the threads executes the work. When we compare this granularity to block granularity, it does launch fewer and larger grids. When we compare it to grid granularity, it launches the child grids more eagerly, because in the case of grid granularity, it has to wait for all the thread blocks to consolidate their work and then does the launch. However, with multi-block granularity, it would launch more eagerly as soon as the multi-block finishes consolidating their work. How do we achieve this code transformation? For a detailed description of how this is achieved, please do visit the detailed description on the paper for the transformation. However, the key differences from other techniques is that every K blocks maintain a shared counter. Each block atomically increases the shared counter when it reaches the launch. The last block to increment the counter perform the launch. And we also use thread fences to ensure the memory visibility semantics are preserved. We put it all together in our compiler framework. So we start always by applying thresholding. So we would have the 4 parent threads here. We can see that work is serialized for 2 of them. Once the thresholding is applied, we apply coarsening on top of it. And once coarsening is applied, we also apply aggregation on top of it. We evaluate our optimizations for 7 benchmarks with 2 datasets each. We report the speed up over a baseline version that uses CUDA dynamic parallelism. We obtain our benchmarks from prior work, and the notation here means no CDP means that we're not using CUDA dynamic parallelism, so there are no dynamic launches. CUDA dynamic parallelism by itself, CDP plus A, which is CUDA dynamic parallelism and aggregation on top of it, T for thresholding, and C for coarsening. So in this case, CDP plus T plus C plus A, it means that we are taking the CDP baseline version, and then we apply thresholding on top of it, and then we apply coarsening, and then we apply aggregation. Our first observation is that not using CDP at all actually performs better than using CDP naively, which is pretty consistent with all the observations from previous work. If we apply aggregation, it also by itself improves the performance of CDP, which is again the same observation as prior work. So applying CDP plus aggregation is about 12.1 times faster than CDP on average per our evaluation. Our third observation is that applying threshold alone by itself, it also improved the performance over CDP, such that CDP plus T is about 13.4 times faster than CDP on average. Our fourth observation is that applying thresholding and aggregation together actually improves the performance even more than applying each of them on their own, despite both of these optimizations targeting the same source of inefficiency. Now, if we go to our fifth observation, we realize that coarsening by itself does not really improve performance over CDP. Our sixth observation is that coarsening, when applied with other optimizations, namely aggregation, it improves performance substantially, because the main benefit was the amortizing the overhead of the aggregation and disaggregation logic. So in this case, applying CDP plus T plus C plus A, which is all of our optimizations combined, is about 1.22 times faster than CDP plus T plus A. Now we profile our work and present the execution time breakdown. Our first observation is that thresholding by itself increases the parent work and decreases the child work, which is expected because when we offset the work, when we serialize the work of the child to be done in the parent, we effectively increase the parent work. The second observation is that thresholding decreases the overhead from launching, aggregation, and disaggregation. And this is also expected because now we are pruning launches and serializing the work instead in the parent. The third observation is that coarsening decreases the overhead from launching and disaggregation. And this was essentially the main benefit of coarsening. which is amortizing the cost of the disaggregation. We also analyzed the effect of imposed by applying the threshold and aggregation granularity. Our first observation is that whenever we are increasing the threshold, the performance does increase until at some point it degrades again. And this is expected because at some point it is favorable to do the work in parallel rather than doing it serially in the parent. Our second observation is that for some benchmarks, increasing the threshold too much will degrade performance. And the last observation is that for different benchmarks, they do perform best with different level of aggregation granularity. As a summary for our talk, we've presented a compiler framework for optimizing the use of dynamic parallelism on GPUs in applications with nested parallelism. This framework of ours includes 3 key optimizations: thresholding, coarsening, and aggregation. Our evaluation shows that our compiler framework substantially improves the performance of applications with nested parallelism that uses dynamic parallelism. It's about 34 times faster than CDP on average. It's about 8.7 times faster than not using CDP at all. And it's about 3.6 times faster than prior aggregation work, namely CLAP. Please feel free to ask any questions. Thank you.